Welcome back. So we were talking about SGD, and I hope we have now a better understanding of what this algorithm is. And in this short lecture, I want to go over two quick examples to see SGD in action, if you will. Okay. The first example is linear regression, and we talked about this when we talked about some basics of machine learning, right? So this is an instance of the regression. We assume that we have some feature vectors, xi's. If it helps, you can think of them, for instance, again as pixels. We have some labels. So our labels here belong to R, so they are scalar. And that's what this typically distinguishes between the regression and classification problems. Okay. And we assume that the regression model, the true model that describes the relationship between the features and labels, is a simple linear model. So something like this, where we may also have some noise in our observations. Okay. And as we talked about, in these kind of examples, we typically use the square loss. Okay. So we look at the regression error, basically, or the mean square error, if you will. Okay. And we want to minimize that to make sure that our model is going to fit the training data well. Okay. Now, this is basically a part of a simple code I wrote using Google Colab. So this is a very useful tool that you can use, especially if you don't have access to powerful computing resources, to run basic machine learning codes, right? So to train basic deep learning models. So in this case, we don't necessarily have a deep learning model. We have a simple linear regression model, which in some sense you can actually think of it as the most simple deep learning architecture. And we're going to talk about this in the future lectures. In any case, so here in this part of the code, we are generating some data at random. That means that I'm generating the features at random. I'm generating the noise at random with certain variance, certain power. And then I generate some true model at random as well. And from that, in this line, I'm going to generate the observations. Okay. Now, this is the part where we are running the SGD algorithm. Okay, so what we are doing in the so first of all, we calculate the loss, and this is a calculation we do typically to see how the algorithm is performing. Essentially, as we're going to see in the next slide, we're going to plot how the loss evolves as we run the algorithm. In the next two lines, we form the mini batch, right? So, and we talk about different ways to do this. We said the simple version, for which we also provide theoretical guarantees, is when you calculate the mini batch uniformly at random with replacement. Okay, and this is the version I'm running this method. Okay, there is also the more practical way, where the mini batches are generated uniformly at random without replacement. Okay, and that is basically the epoch-based version of the SGD that we talk about. And in the next example, we're going to see how that algorithm performs and how its performance compares with this simple version of SGD. All right, so we calculate the mini batch, and then in this line, we basically calculate the gradient, or the stochastic gradient, if you will. Okay. Now, in this case, because our model is simple, we are trying to just fit a linear model to the data. We have a very nice closed form expression for how the gradient is going to look like. In more complicated models, deep learning architectures, for instance, we cannot do this. That's why there has been a lot of development in terms of how to perform this derivative, if you will, in an automated way. And this is something we're going to talk a little bit more as we progress in this course. All right. So after the calculation of the gradient, what we do in the last line, we just update our parameter, right? So this is nothing but the update we talked about before. So the next solution is the current one minus some learning rate times the gradient, okay? And we do this for a certain number of iterations, so capital T number of iterations, until hopefully we converge to a good solution. All right. So here I'm showing how SGD performs for two instances of this problem. where in both cases, I have 100 data points. In one case, the number of features or the dimension is 10. In the other case, the dimension is 200, okay? So in the first case, we are basically dealing with an under-parameterized model because d is less than the total number of data points. In the second case, however, we have an example of an over-parameterized model where d is larger than n. And remember, the second case is what we typically observe in practice. We have very large models. Typically, their size is larger than the size of the data that we have, okay? And in that case, because the model is over-parameterized, we may have multiple solutions to our optimization problem, okay? Now, on the left-hand side, we have the performance of SGD for the first case, d is equal to 10, under-parameterized. And we can see that the algorithm is converging. Why? Because the empirical risk is going to 0 as I'm running the algorithm, okay? Now, we can see some noises here. So there are some tiny ups and downs. And that's to be expected because, again, we don't have access to the true gradient. We have only access to noisy estimator of the gradient, right? So this is basically the impact of the noise in our estimation of the true gradient. All right. Now, something that is a little bit surprising is that for the second case, where d is equal to 200, SGD again converges. So we are still able to reduce the empirical risk, okay? Now, it is less surprising, I would say, in this case, because at the end of the day, we have a convex problem. So SGD can still work well. But in more general cases where we have a highly complex deep learning model, as we're going to talk about, we still observe nice performance out of SGD. Okay, and that's related to the topic of interpolation on over-parameterization that we're going to talk about later on in the course. Okay, so in both cases, we still have convergence. Obviously, when the dimension is larger, the optimization problem is more difficult, but nonetheless, SGD still is able to converge to a solution that is a minimizer of the empirical loss. All right, now let's talk about the second example, and this is nonlinear regression. Okay, so very similar to the previous case, except we have a nonlinearity here. Okay. Now, you should think of this as a very simple neural network with nonlinear activation, for instance, ReLU activation. And these are things that we're going to talk about in future lectures. Linear regression, you can think of it as a neural network with linear activation functions, okay? Where the sigma, let's say sigma of x, was basically x, like a linear function. In this case, sigma is, in the plot that I'm showing here, or in this experiment, sigma is the ReLU activation. So it is something nonlinear. All right. Now, what are we showing here? We are again showing the loss, the empirical loss, versus iteration for 4 different versions of SGD. Okay. The blue curve corresponds to the simple version of SGD that we also provided theoretical guarantee for that. And that's the version where we sample the minimatches uniformly at random with replacement. Okay? And this is performing the worst among these 4 variants. The second curve here, the orange curve, corresponds to SGD without replacement. Okay? So basically we are sampling the minimatches uniformly at random without replacement. This corresponds to the epoch-based version of SGD that we talked about in previous lectures. And we can see here that it performs better than the simple version. And this is something we expect, right? Because when we do sampling with replacement, it is still likely to see a sample that I have utilized in the previous iteration. Okay? So if I feed a sample in let's say iteration 1 with replacement sampling, it is still likely to see that. So it's not going to be quite useful for me. But when the sampling is done without replacement, every batch is going to provide useful and new information. So therefore, I should be able to utilize that and converge faster. All right. So the last two versions we haven't talked about before, and these are what I call ordered SGD, where we're going to be a little bit more strategic when forming the mini batch. Essentially, what we're going to do, we're going to look at either the loss value of a sample in the mini batch or the gradient norm of the sample in the mini batch, and prioritize selection of these samples. Okay? So what that means is that I'm going to sample the mini batches such that the samples have higher loss or the samples have higher gradient norm. And as we can see here, doing so will result in a much faster convergence compared to SGD with replacement and SGD without replacement. Okay. Now let's talk a little bit about why this is a useful thing to do. Why I should look at the loss of a sample or the norm of the gradient when forming the mini batch. So the idea here is that by doing so, we are focusing on harder instances. And focusing on harder instances is going to accelerate the training, as we saw in the previous slide, because we're going to be able to find the boundary sooner. Okay? So let's discuss this in the context of classification. Imagine that I have a classification problem. In this case, I'm showing a simple binary classification problem. So what's the goal? Essentially, the goal is to separate class 1 from class 2. So I'm looking for a separation manifold, such as this. So this you can think of it as my model. So after the training, I'm going to be able to find a model like this, which could be a nonlinear manifold that results in the separation of the one class from the other class. Okay. Now, if my goal is to find a model like this, it should be intuitive that samples that are closer to the boundary, such as this sample or this sample from one class, and let's say this sample and this sample from the other class, are more informative than the samples that are further away from the boundary. For instance, this sample and that sample. Because when I focus on the samples that are closer to the boundary, I should be able to find this separating manifold faster. And this is exactly what is happening in our experiments from the previous slide. Okay? So it is useful to focus on hard instances. How can we quantify hardness? Well, a natural way is to look at the loss values or the gradient values. Okay? Because if the loss value is hard, that means that my model is not able to fit this sample easily. So it should be a hard sample. And a similar statement can be stated for the gradient norm. Okay? So that's the reason that those two methods were converging much faster than the simple versions of SGD. Okay? So this also is a good point to talk about trade-offs that we observe and have to deal with when we are optimizing deep learning models. Okay? So in this case, a natural trade-off is the trade-off between performance, how fast I'm able to minimize the function, and robustness. Okay? So when I put my focus on the samples that are closer to boundary, I may get a solution that is not robust. Why? Because imagine you are dealing with a scenario where the labels are noisy, and this could arise in practice very, very often, right? So if you are dealing with scientific data, you should expect to have noisy data points. Also, many times when we are labeling, let's say, data sets, that process could be erroneous. Okay? Even for very carefully put together data sets such as CFAR10 and CFAR100, there are instances that are mislabeled. Okay? Now, the chance of mislabeling intuitively is higher for the samples that lie near the boundary. Okay? So if we are focusing on the samples that are near the boundary, and it happens that those samples are noisy, then our solution is going to be wrong, meaning that it's not going to generalize as well as we hope for. So therefore, it's not going to be a robust solution. So there are articles in the literature that advocates focusing on easy samples for robust training. So this is exactly the opposite of what we just mentioned, right? So it therefore depends on what your goal is, right? And what's the context. If you know for a fact that the data is very, very clean, it is a good idea to focus on hard instances, like the previous experiments we saw in the previous slide. However, if you expect to see some noise in the data, you may want to focus on easy examples, right? That could mean that the performance is going to be slower, but you may gain nicer robustness properties. So this is basically a trade-off between performance and robustness. And indeed, there are many trade-offs like this between performance and other contexts. For instance, a trade-off between performance and fairness, or performance and privacy, and things of that nature, which we're going to talk about later in this course. So hopefully this gives you an idea of how SGD performs for basic problems. In the future lectures, we're going to talk about some variations of SGD that basically aim to make SGD a little bit more stronger. I'll see you next time.